All right, let's do this. So we are going determination of specific latent heat of vaporization. So if you do not remember, I'd like to remind you here that specific latent heat of vaporization is basically latent heat of vaporization is the phenomena where a liquid changes to gas and gas changes to liquid. This is what we should be knowing. All right. So I've also given you the definition before. Now we need to basically draw the the whole diagram first. Usually what happens is, in this diagram, you need to have a pan balance. Let's draw it like this. Generally, we draw pan balance like this. Important for paper 4, paper 5, like I said before. Then on top of this pan balance, you guys need to keep a beaker, okay? In that beaker, you need to place a heater, and then just take out 2 wires from that and connect it with like an ammeter, because we want to monitor the current. Then in series with the supply, and then in series with the variable resistor. Variable resistor is important because we want to control the amount of current or the power in this. And then connect it like this, okay? Like that. Then what you're going to do is just make across the heater, you also need to have a voltmeter to monitor the voltage that is being supplied to the heater, like that. All right. Once you've done this, so here we have immersed heater in the beaker. Just symbolize that this is water. So let's now start writing. So this is ammeter. This is voltmeter. This is power supply. This is the variable resistor. This is the low voltage heater. We want to keep it low voltage because we do not want the water to be heated very quickly. So this is the boiling water, and this is the pan balance. Who knows what pan balance does in this class? Can you please tell? Anyone?
It measures the weight.
Measures the measures the mass. All right, it
Yes.
measures the mass. Okay, now this is the working drawing of the whole thing. Okay, so this is quite simple. All you guys need to understand is that when you have this sort of arrangement, obviously the heat energy is supplied by heater. Okay, so this is the total input energy that we're looking for. So this is input. This will go into your output, which is the energy used to vaporize water. This is your output energy. So we're just making that, energy conservation equation. Plus some energy is going to be energy loss to the surroundings. So this is going to be your wasted energy that we need to figure out. Now the interesting part is that we do not want to do anything to the temperature, because The fact here that you guys need to remember is that water, okay, so liquids or anything boils at constant temperature. So you don't need to maintain the temperature like we did yesterday for the other one, for the specific heat capacity. So, which means we can take two readings, reading 1 and we can take reading 2. In the first reading, I'm going to take one set of equations like you can take voltage 1 and current 1. We can change it by variable resistor. And then for some amount of time, we can actually give it the amount of energy. So let's suppose for 5 minutes or something like that. So this will be power into time. Then energy will be, equals to. Now, we are going to check within this 5 minute time or whatever time it is, how much mass has changed. So this will be the mass one that we have checked. For example, it showed us 100 grams initially, and after 5 minutes, it became 80 grams. So now the mass that is basically boiled or vaporized is 20 grams. Do you guys understand that? So M1 will be then 20. Is it clear? This is just an example. So that is M1, and then latent heat of vaporization is mass times latent heat of vaporization. That's what we need, and the amount of heat loss will be H. So let's write that. Then we are going to change the current and the voltage, and when we do that, so obviously because of less or more power, there will be a different amount of mass that is going to vaporize this time. So M2 times LV, but this latent heat of vaporization is constant, so it will stay the same. Also, the heat that is being lost to the surroundings is the same. When you have two sets of the reading, then what you're going to do is you're going to subtract these. When you subtract, it is going to be like this. V1 I1T minus V2 I2T. This will give you M1 minus M2, so the change in mass times LV, and minus basically this will become H minus H, which is 0. Is it clear, everyone? Please let me know if you have a question here.
It's clear.
Oh, okay. So, Zainab, you have done vaporization. Like you know what is vaporization from IGs?
Yes, sir.
Okay. All right. Do you understand how we have done this?
Kind of.
Okay. It's all right. So again, I'm telling you something very important. When you see a drawing in your exam that is not, say, insulated, when it's not insulated, it means obviously the heater is supplying energy to the water for it to boil. All right, Zainab.
Yes, sir.
But the issue is because it is not insulated, so some of the heater energy is also going out in the surroundings, right?
Hmm.
Now, you might know already that heat always travels from high temperature to low temperature. You know this? So
Mm-hmm.
suppose inside water boils at 100 degree, we know this, and outside temperature is maybe 30 degrees. So obviously the heat from the water will go out. You get it?
Yeah.
Now, how much heat will go out? We do not understand. We do not know that. So we are just keeping it as H. Is it clear?
Hmm.
And basically, the energy required for latent heat of vaporization is LV times M. What is M? The amount of mass that is evaporated. How do we get to know about this? By seeing what is the mass change in this pan balance. Is it clear?
Hmm. So, what are we trying to like find in all of this?
The latent heat of vaporization. That's determined.
Okay.
Okay. So, where did we get voltage, current, and time? What is this? You should understand that basically power of an electric heater is VI. You agree?
Yep.
Power into time is energy, so we can write energy supplied by the heater will be VIT. So this is the energy supplied by the heater. which goes into evaporating this and also losing some energy to the surrounding. Do you get it?
Yeah.
Now, the good thing is that when we increase the power or the energy supply or decrease it, doesn't matter, it will only change the amount of mass that is going out, right? The
Hmm.
latent heat of vaporization for water is the same quantity that we're finding, but the energy loss is going to be same as well, because no matter what, water always boils at 100 degrees. So the difference between the outside temperature and the inside temperature will be the same, which means the heat that always is lost as H will be the same in every reading. Is it clear?
Hmm.
By taking two different readings, what are we doing? We are going to subtract them. When we subtract them, so this is like energy 1 minus energy 2. This will be mass 1 evaporated minus mass 2 times LV. And this becomes actually 0 because it cancels out the effect of losing heat. Get it?
Yeah.
So by taking two readings, we are basically looking at that. Is it clear, Zainab, now?
Yes, sir.
Okay. Everybody, if you have any questions still, Amna, how are you? Please let me know. Sameer, everything is clear? Afan?
Clear.
Okay, now going to the next, okay? Now, when you look at the last part, where we need to determine the specific latent heat of fusion of ice. So, determination of specific latent heat of fusion of ice. Okay. Now, please understand this. Again, draw the diagram. It's very important for paper 5. You won't be able to get it later on, and just learn this now and do it how I do it very neatly, because the examiner doesn't like, people who have just done really bad drawings. All right. So first of all, pan balance in this. Then you got to put a beaker on the pan balance like that. Uh-oh. That's not fair. Wait, like that. And then on top of it, you need to put a funnel. I don't know what it's called in chemistry, but I call this funnel. So I think it should be called funnel, I think. But you guys can tell me better. Okay, so this looks like this. And what you got to do is you got to add some ice on in it. So put a low voltage heater first, like that. Okay, heater should be drawn. The heater symbol is like this, so it has like two bars in the middle, right? So it should be three boxes in the center. This is heater symbol, like that, and this. And now just make the whole circuit. So the circuit would include, like I said, an ammeter. It should include a power supply. It should also include a variable resistor, because we want to make sure the current can be changed and so is voltage. And then within this, just take it on the other side and here, okay, and connect it like this. And then just put voltmeter across it, because we want to measure the voltage of the heater. Then what you got to do is you got to fill it with some ice, which is melting ice basically, like this. And you guys know that this melting ice will start to drop like water onto the beaker, like here. Is it clear, everyone? And it starts to melt. So now let's label this. What we need is we need a low voltage heater first. We need crushed melting ice. We need, this would be ammeter, this would be voltmeter, this would be variable resistor, and that's going to be power supply, like that. This is your collection beaker. Uh-oh. अहमद बेटा ये जरा इसमें चार्जर लगाओ. And then this would be your funnel, and this is your pan balance. Pan balance to measure the mass. All right. Now this is far most the easiest one to find out. Now, obviously, no matter what, the lab you will be working on will have energy that is supplied from the surroundings to melting ice. So in this one, how is the equation made? Let me just write it down here. So the equation will be energy supplied by heater plus energy gained by surrounding. This time surrounding is helping the ice to melt. Energy is not going to the surrounding. So this is something very important to remember. And what is it contributing to? Energy absorbed by melting ice. Is it clear, everyone? So this is the only difference, right?
Yes.
Now what will we do here? So let's suppose we want to find in the reading one, we will not turn on the heater, so we will say the heater is turned off. So I'm gonna put okay, let me write reading 2 as well, so that in one go then we can do. So in the first part I'm gonna get no energy from heater, and the reason why I'm doing this, I will basically turn off the heater. So when I've turned it off, now the only source of energy for ice to melt is the amount of energy that comes from the surroundings. Is it clear? Do you guys understand that?
Yes.
Yes.
And this energy is basically going to give us latent heat of fusion times the mass m. What is this mass m? This mass m is the mass of ice melted due to surroundings. Is it clear? Like that. Now, in the next part, what you're going to do, we're going to turn on the heater for, let's suppose, 5 minutes or whatever. So this also should be done for the same time. So in here, write a note that in the first step, I will turn off heater for 5 minutes. All right, and collect mass of melted ice. All right. Then in the second part, you're gonna turn on heater for 5 minutes as well. Now you want to keep the same, the time so that it's fair. So when you turn on the heater, obviously heater will take voltage, some current, and time, which is 5 minutes here. Also, it will gain the same amount of energy in this 5 minutes. This will now, if this is m, this is m, and then this will now give you LF times. Let's write it capital M. What is capital M? This is the mass of ice melted by heater plus the surroundings. Do you guys understand this?
Yes.
So when you subtract this, you realize that basically it will be h and h will cancel out. It will be only VIT minus 0, and h minus h is 0, equals to m minus m times LF. Do you guys get it? Now this value that you see here, this is basically the mass melted due to heater energy only, because we have subtracted the one that was melted due to surroundings. from their total mass. Is it clear?
Yes, sir.
So this is the sort of method that we are just using to cancel out the effect of the surroundings. So we get the very pure and exact value of latent heat of fusion here. So you can basically write this down, and then we're gonna see what type of questions they give us in this. Khatija, Irfan, do you understand that?
Yes, sir.
Mass melted due to heater energy only. Okay. All right. Samir, you okay? Laiba, Dania, everything is clear? Abdul
Yes, sir.
Rahman, Amna? Okay, very good. Very good. Excellent. Very good, Dania. Very good. Now, should I go to the question?
Yes, sir.
Yes.
All right. Let's check it out, huh? What we got? Okay, let's see what is the first question we'd like to see. Okay, so, chalo. Let's copy this first. Already we have it. Okay. Wait a second, people. And then the next question is actually the one we have just done. So we'll copy that too. These questions are often repeated, so and they are very similar types. So if you practice 3, 4, I don't think you will feel any difficulty in any of these. Okay, go on, please. Here, all right. Let's close it now and look at the first question. So in the first part, it says it says basically you need to define what is specific latent heat of just specific latent heat, no fusion, no vaporization. So we're gonna just define it in general terms. So in general terms, we're gonna say heat energy required per unit mass. So this will give you 1 mark because specific means per unit mass, right? And then you say that to completely change, so this is the second mark, okay? To completely change state of this mass at constant temperature. Now, I would like to tell you the two keywords in this definition are number one, when you write per unit mass, this is for the first mark, and the other to change the state at constant temperature, because whenever state is going to change, it will be at constant temperature. Now, I would like to also comment on something here. If you have written everything correctly from this point to this point, everything is fine, but you have forgotten about constant temperature, you will get no marks. This constant temperature carries an A1 mark, and the other one is M1. So in basically exam, you need to understand whenever something an answer attached with the method mark, so they are interrelated, which means if you forget one of these points or you have not written the required keywords, you will not receive any mark. So it's 0 or 2. It's nothing in between. So please do remember this. This is very tricky here. Okay. So please write this definition so that you guys know exactly what to write when this definition comes. Now, since they have also written in this, as you can see, they have just generalized it to specific latent heat, then you do not need to. If you write vaporization fusion only or definition about that, that would be wrong, because they're not asking about a specific change of state. They're asking about all change of state. So make sure to generalize it. Okay. Now let's go forward. If you guys have no questions, let me know. Now let's see. First of all, it says this is the similar type of the experiment that we've done. It says an electrical heater is immersed in some melting ice that is contained in a funnel. The heater is switched on and the ice is melting at constant rate. The mass m of ice melted in 5 minutes is noted. Okay. And then together with the power P of the heater, the power P of the heater is then increased. Now this time he's not taking about surrounding. He has increased the power. That's the same thing. Don't worry. A new reading of mass m of ice melted in 5 minutes is recorded, and the ice melting at constant rate. Now they've given the data. They've said when I used power of the heater at 78 grams melted in 5 minutes. So he wants us to find the mass melted per second. So 5 minutes, the time in 5 minutes is 5 into 60. So that's going to be, I think, 300 seconds, right? Let me take out the calculator, please.
Yes, sir, it's 200.
300, yeah, okay. So it means it is in 78 when divided by 300 will give us 0.26 grams melted per second. Is it clear?
Okay.
Now, same thing you're going to do for the other one. So at this power, we have this much grams. So we're going to do 114 divided by 300. So it's going to be 0.38 grams per second melting. So we got this done, right? So remember, this is basically what they've given is they've given mass per unit time, mass melted per unit time. Now let's go forward. It says complete the data. We've already done this, so that's good. Use the data in the figure to determine the value of specific latent heat of fusion of ice. Now I need to create that equation. What is that equation? Equation is that power of heater, sorry, let's write it this way. In terms of energy, it is easy. Energy of heater plus energy of surroundings will give us the energy required to melt. Okay, so this is the main energy conservation equation. So what is the energy of equation? We have only this much. This means that basically this is 0.2 grams melted in a time of 1 second. So power was 70. We're going to multiply it with 1 second to convert it into energy. What am I doing? I'm doing power into time. Then the surroundings was H. Let's keep it as a symbol. And the other one will be latent heat of fusion times the mass melted was in 1 second 0.26. Do you guys understand this?
Yes.
Now, how do I basically know? How do I know that I have to use grams and I don't need to change into kgs, because in the answer it is already given that I need to write it in grams here, right? So what you do then? You basically do 70 plus H equals to LF times 0.26. Now you have to do the other one. So the other equation will be power into time. The new power was 110. In 1 second, it basically the energy that was lost to this gained from the surrounding was H, and LF times 0.38. Do you guys get it? So I get 110 plus H equals to LF times 0.38. The next thing we're going to do is we just need to subtract these two equations. So I don't have much in the actual with these topicals that are made. They're basically shrinked. That's why we don't have much space, but it's all right. We can do it in the other section. So the equations that we are left with are 70 plus H equals to 0.26 LF, and 110 plus H equals to 0.38 LF. When you subtract these two, it will be 110 minus 70. H and H will cancel out, and 0.38 LF minus 0.26 LF. Can you please find it? This will be, I think, 40. This will be
The
0.
final value for LF is 333.
Sorry.
The final value for LF is 333.
Okay, so 323 joules per gram would be your answer. 323.
333.
333. Okay. 333. Anyone who could not understand this, please let me know.
Sir, the power over here is constant, right?
Which is constant, sorry?
The power.
Yes. No, no, not the power. It's the it's basically the energy that is gained from the surrounding is constant.
So like if we used 5 minutes instead, could we do it that way? Like
We could
math
have done
wise?
that. Then we would have taken this mass.
Uh-huh.
You could have written this as this much power into 5 into 60. So this will be the time. Power into time equals sorry, plus H equals to now LF times 78. You have to do this then. You get it?
Hmm.
Now this already means that basically it is grams. How much gram of water ice is melted in just 1 second? That's why we are multiplying one here. You get
Yeah.
it?
Hmm.
Yeah. Now once you have this, in the next one it says you guys need to find the rate of thermal energy gained by ice from. Rate means that they require power. Rate means thermal energy was H. When you divide by time, it will give you the rate. Is it clear? In order to do that, obviously we need to use one of these equations. We already have LF now, right? What you want to do is take maybe 70 in 1 second plus H equals to LF is 333 and the melted ice was 0.26. Can you please find H now?
I'm getting 16.7.
16.7 uh, joules, right? Now to find this H, what we need to do is we just need to divide it by 1 second because that was the time. So that would give us 16.7 watts. Is it clear, everyone?
Yes,
Yes.
sir.
This is as simple as this. You don't have to do anything. You just need to follow the whole like this the same setup, and you will get the right answer. So this is pretty good in that sense. Now let's go and check the next one. If you guys have written this, or even if you have not, that's fine. You can do it in the worksheet. Now let's check this one again. As you can see, he has asked for this definition again. The three keywords were per unit mass. I'm just writing keywords so you do not forget. Per unit mass, change in state at constant temperature. So these are the three things you got to write. So 1 mark for this, 2 mark for this. So just remember this. Anyway, now going forward. So this is a very similar setup that we have basically learned, and says the heater of power 110 watt is immersed in the liquid. The heater is switched on, and when the liquid is boiling, balance reading M are taken at corresponding times. T. Okay. A graph of variation of time T of balance is shown. So this time they're given a graph. It doesn't really matter. What you guys need to understand is that in this one, when the time had not started, the mass that basically was in the beaker was this much. So this is the initial mass. Do you guys get it?
Yes, sir.
Yes.
I don't know what this is, huh? Let's check, huh? So I think
I'd
one,
say
2, 3, 4,
372.
5. This 370? That's 372. Okay, that's good. So this would be 372 grams. All right, very nice. Now these are things I check all the time when the graph is given. Also, the time is in minutes, which means probably we need to change it later. Now it says state the feature which suggests the liquid is boiling at steady rate. Who's gonna tell me this?
May I?
Yes, please go on.
First of all, the gradient is constant, straight diagonal line, which indicates that with equal changes in time, there is a constant decrease in mass.
Yes, so we can basically just write it with one mark. You don't need to write so much detail. Just write it has a constant gradient, which means that for equal intervals of time, there is equal change in mass boiling. Is it clear? Okay.
Yes.
Now then it says use the data to determine a value of specific latent heat of vaporization of the liquid. Fine. What you should do is you should always try to pick the first and the last value, or you can also pick any intermediate value, because obviously the constant gradient means that you don't really need to do anything. But generally speaking, in my experience, usually what they do is you can actually pick the last one, and they always take the last one as their value. So if you really want to go through the mark scheme stuff, otherwise you can obviously take any other point. So just mark it. You might see that within this change in time, which is I think 7 minutes, how much mass is melted? Let me see. This is in the middle, by the way. 322, 324, 326. So this will be 325. You guys agree?
Yes, sir.
Yes.
So we got 325. Now the mass change would be 372 minus 325. What is that? Can you please help me find this?
48.
47.
Sorry?
47.
47.
47 grams. All right. And the time is 7 minutes. So I'm going to change. I'm actually, it's kg and joules. So what I got to do? First of all, I got to change this. So I'm going to divide by 1000. It's going to be 0.047 kilograms. And 7 into 60 is 7 into 6 is 56, right? So 560 seconds. Is that would be the time. Now, what is the equation? We're writing energy supplied by heater should go to melting of ice. Latent heat to melt. Okay, to boil. Sorry. All right. So this will be power into time, and that will be latent heat of vaporization times the mass. So power was basically, let me change the color so we have a bit different. 110 times 560 seconds equals to latent heat of vaporization, and the mass was 0.047. Can you find latent heat of vaporization, please?
I'm getting 1.3 times 10 raised to power 6.
Yes.
1.10
1.3. 1.3 times 10 power 6.
Yeah.
power 6. Okay, joules per kilogram. All right. Okay, so now, let's look at this. It says now you might have like seen that I have not added H in this, which is the energy lost to the surrounding. That is actually intentional. The reason why I'm not doing this, because in the very next question says, state with the reason whether the value determined into is likely to be an overestimate or an underestimate. If they want us to include age, they would never ask this question. So be smart and don't try to solve that. All right, because then you have to take the other reading. We can do that, but it's not important. Now it says, what do you think? It's an overestimate or an underestimate?
Overestimate.
Overestimate.
Why?
As
Why?
some of the energy should be lost to the surrounding as well.
Yes, it is an overestimate because by not adding age, what we're doing, we're actually thinking that all this energy goes into this, which is not true, which means it should be an overestimate, that we are thinking that larger amount of energy is going into a boiling, which is not true. Overestimate as some energy from heater is also lost to the surroundings. Any person in this class can please let me know if they do not understand that. Oh, that's a good. Sorries. Okay. Please let me know if you have a question here or you do not understand something. Okay. Latent heat of vaporization. Wait a second. This value 372 minus 325 is 47 divided by 1000. Done everything right. 110 times 7 into 60 and then divide by 0.047. Okay, this is not the value that you guys have calculated wrong, by the way. It should be 9.83 times 10 raised to power minus 5 on my calculator. Why is your value different? Can you please recheck? How's that even possible? Let me check again.
I think we got 560 wrong. 7 times 60 is equal to 420, not 560.
Yes, that's why. Okay, so it's basically all right. So it should be 110 times 7 into 60 power into time divided by 0.047. Yes, that should be the answer. Please correct this. All right, everyone. It means my mental math is as bad as your mental math. That's very bad. Anyway, so lesson learned: do not do mental math in your paper. Okay, so uh, all right. Okay, so this is basically the thing that I wanted you guys to understand. Now, I'm going to give you an assignment on this because if you practice all this, I don't think you will be able to make a mistake, especially like in the conceptual one. Let me just put an assignment here. So then let's just put everything here. Today, Abu Bakr is like on leave. Otherwise, he would say, "Sir, so long." Wait a second. Some of the questions I've already done. You can skip those. But if you want them, if you want to practice those, you're most welcome. Otherwise, you just need to submit the other questions. And now that you guys know that you get a message after a whole month when you've not done the assignment, so it's a good thing to do it before your parents know. All right. So we are going for uh, fusion and specific heat and latent heat. Okay, so here you go. And now this chapter is basically quite long because this is one of the major chapters. I just wanna basically tell you that you guys just revise this up till now, whatever we have done. We will continue on Monday. On Saturday, however, I'm just writing it here, so you guys should remember that as well. So last week I was supposed to take your test, but I did not. Saturday, and the date I think on Saturday is, I don't know what is the date. 19th 19th August. Okay. Saturday 19th August, test of ideal gas. Okay, this is the chapter we've done quite long time. You've also done the worksheet. I've probably checked it as well. So test of ideal gases. Please prepare that at 5. Sorry, at 5:30 Pakistan time.
Sir, that makes it 3:30 KSA time, and I won't be available at that during
You
that
won't be
moment.
there.
No, it's the back to school season, so I have to go for the usual uniform and stationery shopping. I won't be available all the way from 2 o'clock Pakistan time to 7 o'clock Pakistan time.
Saturday, everybody has an off, right? So we can do 12:30 p.m. AM. Sorry, 12:30 p.m. Pakistan time. That would be fine. Okay. Any issues now?
No,
Okay. So that would be the test. Please make sure that you revise it, ideal gases, and then let's meet
all right.
again on Monday.
Allah Hafiz.
Okay.
So,
Yes. क्या नाम है? Zainab, I want you to stay back. Okay. Zainab, wait a second, please. Okay. Zainab,